All right, so there's three general categories of problems, and it's important to be able to identify what type. So we had like what would just be the basic speed up, slow down ones that we started with, like was on the first quiz. We had two-part problems and we had free fall problems, right? So especially for the two-part ones, I told you this the other day. If you don't identify it right, you're probably going to miss a lot of points on that kind of problem on the test. You don't even attempt it as a two-part problem, right? So make sure as we go over these today or when we get to some of the two-part ones, pay attention to how like you could figure that out if you're not sure. So 80 would be like one from the very early on. All right, pretty straightforward. It says find the uniform acceleration of a car that causes a car's velocity to change from 32 meters per second to 96 meters per second in an 8-second period. So if V initial is 32, always make sure you look at your units too to make sure they mesh. VF is 96, and the time is 8 seconds. We want to find the acceleration A. Always consider the fact that sometimes you might have to make things negative. Doesn't sound like anything needs to be negative in this problem. So A is equal to, well, the equation 1 is what we would use here. VF equals VI plus AT. Nothing zero, keeping it around and rearranging is A equals VF minus VI over T. Plug in the numbers, and that's 96 minus 32, which is going to be 64 divided by 8. 64 divided by 8 is 8. What's the units on acceleration? Carson. Meters per second squared. So pretty straightforward. Nothing really tricky about that one. Just make sure we got your right units. Keep remembering also when picking out givens in any style problem. You know, meters per second has to be a velocity, right? Don't ever list those as an A. If it was A, it's in meters per second squared, right? Time obviously is in seconds. D's are obviously usually in meters or kilometers. You might have to convert, but like make sure it's a sensible unit before you think about it before you write it down, so you don't make mistakes like that. And should go without saying, but one, the probably most important thing is identifying what you got to find. And there wasn't a lot of big mistakes on the first quiz on this stuff, but anybody who did miss any significant amount of points, other than just a small point here or there, which was not identifying correctly what they were supposed to solve for. But that usually should be easy. You're just being careless if you don't identify what you're supposed to solve for. If it asks for how far, that means D, right? It straight up says find the acceleration. Well, what more could you be told? Find the acceleration, right? Make sure you solve for what they're asking. Otherwise, you're going to get very little points on the on a problem on a test or quiz. So read it carefully. That shouldn't be an issue, but sometimes it is. All right, other one. What do we got? Levi. 107. Okay. Doesn't matter the order we do these in. 107, we're flipping over to page 83. It says a baseball pitcher throws a fastball at a speed of 44 meters per second. The acceleration occurs as the pitcher holds the ball in his hand and moves it through an almost straight line distance of 3.5 meters. Calculate the acceleration is the first thing. The other thing is just like consider kind of thing. But sometimes you have to imagine the motion. Remember what I said from day one. Don't just make this only a math problem where you rip out numbers and don't think about the situation. Because sometimes that's not going to work. You have to actually think of what's going on. When you throw a ball, you pull it back, and for a moment before you come forward, you do what? So from back here, this starts from what? 0, right? So you got to, it's not jumping out saying that, but you got to think of the situation, and that makes sense to say that, right? So VI is 0, and this pitcher is going to pitch it, release it, get up to a speed of 44 meters per second. And this happens over a D of 3.5 meters. Now that might seem kind of far, but we're throwing a pitcher's wind up. It's not just like throwing it like that. When a pitcher winds up, they lean back. It starts way back here, and by the time they release it, they take a big step. It's right here. So a fairly tall person, it's totally reasonable to go over 3.5 meters to the point where they release it. All right. And from all that, we wanted to find the acceleration. So units all look good. Don't have to convert anything. We got VI, from what our givens are unknown are there, we would go to equation 3, which is VS squared equals VI squared plus 2AD. VI is 0, so we could get rid of that before we rearrange. So A would be equal to VF squared over 2D. Plug in our numbers, 44 squared divided by 2 times 3.5. Run those numbers. And remember, all the numbers I posted, answers I posted, were from the book, and they're all done in Sig Fig. So as long as you were really close to those, I'll run the numbers, see what we get out here. 44 squared divided by 7 essentially. You get out about 276.6 meters per second squared. The book answer was 280. That's definitely within reason close as far as you're not because of 60. Now, that's the main part of the problem. The other part was just really, you could have wrote something out, but really just to think about something here, right? This was not a free fall problem at all, right? It was a normal, like early one really, of acceleration, speeding something up. But it does say compare this acceleration to that due of gravity. The point of here of them asking that question is this a concept thing. We think of gravity probably as a pretty strong force, don't we? Right? But if you really think about it, it's not as strong as you think. Right? Gravity accelerates things at what number again? Yeah. Right, negative 9.8 meters per second squared. And for the reasons of asking this, the magnitude is all that really matters. 9.8 meters per second squared. Oh, gravity is this really strong force, right? Well, a human being just accelerated a ball at almost 280 meters per second squared. Is gravity as strong as you think it is? No, it's really not. I mean, if gravity was as strong as what we sometimes consider, you wouldn't even get up out of your chair, would you? You always defy gravity or go against it, right? I'm standing up. I just did. I had to accelerate faster than that to get up. Otherwise, if I couldn't, then I wouldn't have been able to get up, right? So it's just a question to think about. And the main part is being able to solve that problem. And that's kind of why they asked that and posed that question. Is that we do things daily. Everybody in here does things daily that accelerate things way more than gravity does, right? But as far as like the solving that, we good on that? All right, other ones. What else? Waken? Which one? 91, okay. I think that was one of the two-parters. All right, the very first two-part problem we did as an example was a lot like 91 and 95, right? Where you're driving along and something jumps out in front of you. You notice something in front of you, right? Remember the situation. Why is this a two-part problem? Because when you notice something is in front of you or something appears or jumps out in front of you, do you immediately hit the brakes, like instantaneously? No, your brain has to process it, right? And during that time of, oh crap, I gotta hit the brakes, you still go at whatever speed you're going at, right? That would be a constant velocity. So two-part problems, there was variations of them too, that wasn't only type. But two-part problems have one part constant velocity and one part speeding up or slowing down, in other words, acceleration, right? So if you identify a problem that has part constant and part acceleration and try to solve it in one piece, that's where you're gonna miss a ton of points. You've got to be able to read and just identify that from the situation, all right? So this would definitely be one of these because in 91 it says the car is traveling at 20 meters per second when the driver sees a child standing on the road. He takes 0.8 seconds to react and steps on the brakes and slows at 7 meters per second squared. How far does the car go before it stops? So this one's almost identical to the example we did back then, all right? These different numbers. So we have constant first because we didn't hit the brakes yet during that small amount of time. 0.8 seconds. So remember what we did back then. We made a little column. Constant V and variations of problems, the acceleration could have came first, right? But in this particular problem, it was constant V, then we slowed down, so that's the accelerated portion. So watch out what we put in each one. So the constant V we were traveling at was 20 meters per second. The thing jumps out in front of me, and I had to process for 0.8 seconds. And while I'm processing to hit my brakes, I'm still going at this. So again, that's why it's constant. And then over another column, here's where you got to be super careful, guys. Does this T have anything to do with your stopping time? Does that T have anything to do with your stopping time? No. That's how long it took you to react to hit the brake. Not how long it took you to stop the car. You could not cross over that piece over here. You got to understand that. All right? But what can cross over, when you hit the brakes, you were going at this speed, right? So that constant V from there becomes my VI over here, right? Remember doing stuff like that? And I'm going to hit the brakes to try to stop, so my VF is 0. And the A they gave me was 7, but we got to be careful. What do I got to do to that A? Well, make it negative, because if I'm going in an assumed positive direction, I am, as long as I set this like this, which we're supposed to do. Assume we're going positive unless told otherwise. Then my A's got to be negative if I'm truly slowing down. If I kept that positive, that would mean I'd actually try to speed up when something jumped in front of me, which I didn't do. So like we've always seen many times in the past, sometimes we got to slap an A or a negative on that A, so be aware of that. All right. So at this point, once we all got the givens in each column, I got to find the D in this one and the D in this one, right? This was part 1 of the problem, so I could call that D1. This is part 2, I could call that D2. Remember, the only formula that applies, the only option you got for constant V is the formula V equals D over T, right? So we've got to use that one. And if we rearrange it, it's D equals V times T. You simply pop those in. That would be 20 times 0.8. So 20 times 0.8. That's going to be 16. Go on to this one. We got to find the correct kinematic equation. That would be equation 3, which is VF squared equals VI squared plus 2AD. VF 0, we could get rid of that, solve it for D. We'll subtract over VI squared first, divide by 2A, and plug in the numbers. So this D for part 2 will be 20 squared over 2 times negative 7. And for that part, we'll get 400 divided by 14. It'll come out positive because the negatives will cancel each other, and that comes out to be 28.6 about meters. And what do we do with this answer and this answer now to finish this off like we did in the past? What do we do with that D and that D, guys? Yes. Add them together because we wanted the total stopping distance, right? So this was practically an exact copy of one of the old examples we did. So we get about 44.6 meters as a stopping distance in number 91. Close to 45, which is the 6th answer. That's a pretty typical 2-part problem. You okay with it? Definitely did several like that in the past. Alright, other ones. Keep going, Smith. 115, okay. Now this one, it's still probably the trickiest one there, especially part C. Part A and B I don't think is too bad. Part C is the one where something might be easily missed. But anyways, let's jump into it. A helicopter is rising at 5 meters per second when a bag of cargo is dropped. The bag falls for 2 seconds. What's the bag's velocity? How far has it fallen? And how far below the helicopter is the bag? So let me draw a little diagram here. Here's my helicopter. Don't laugh at my helicopter. So I'm going to draw a little dotted line here. And this dotted line is going to represent the drop point. This is where it happens, all right? But the helicopter, the whole time it was told, is going up, right? Did it ever say the helicopter ever stopped moving upward? You got to consider that, especially for part C, all right? So, and this is the moment that it's dropped, and of course that bag or whatever's dropped is going to go that way. But after a certain amount of time, what's the time here? After 2 seconds, the helicopter, if it keeps moving, is going to be somewhere up here, right? Because it never said the helicopter stopped after it dropped the object, right? So after two seconds or whatever amount of time, it's going to be up here, and this thing, the thing it's dropped is going to be lower than that level, which is my dotted line, right? Just to get a conceptual idea what's going on. Make sense? All right, so let's put in the exact numbers and see what we got to find here. So we've got the helicopter itself is rising at 5 meters per second. So I'm going to actually make two columns here. The helicopter and the bag we dropped. You'll see why in a second. The helicopter's V is a constant V. It's going upward all the time at 5 meters per second, right? Now here's where we're going to be careful. The first thing asked is what's the bag's velocity after 2 seconds? So its final velocity after 2 seconds is part A is asking, right? Well, the bag, it was dropped. But was it dropped from rest? No. If it was just dropped like I dropped this here, what would be the VI of the bag, guys? Yeah, 0. But that was another little tricky part to this problem where you got to read it very carefully and think, all right? It was dropped from a helicopter that was rising how fast? 5. So the VI of the bag isn't 0, it's 5, isn't it? I kept stressing this in the past, knowing that this problem was coming. VI is 0 for dropped if you're positive it was dropped from a stationary place. But it was dropped from a rising object, so it's whatever, when it was dropped from there, it was going whatever that object was going at, right? Now, it was dropped, so we could say that the bag is in free fall, so G is negative 9.8, right? And we know the T is 2 seconds. So we've got enough to find VF using all that. Make sense? So we will use the second, not the second, the first equation. VF equals VI plus AT, or for free fall it's GT, right? Because G is this specific A like we said. So we don't even have to rearrange. We plug in 5, all my units are good, plus negative 9.8 times 2. And I get out negative 14.6. Why does it come out negative? Because which way is the ball falling after 2 seconds? Down, right? It's on the way down by then, and that's meters per second. You okay with that part? So as long as you got the VI was 5 and not 0, that should be not, other than that little detail there, that was a pretty basic free fall problem once we know what the VI was, right? So part B is next. Part B says, how far has the bag fallen? So we could use all the same information up here, but this time solve for what? How far is it? Yeah, D, right? So this one's D. Try to use only givens as possible. So I'm going to try to avoid using this number if possible, okay? Using this, that would be equation 2. And D equals VIT plus 1/2 GT squared. Plug in the numbers, that's 5 times 2 plus 1/2 times negative 9.8 times 2 squared. We're going to get out negative 9.6, and negative just represents that it's on its way down. And technically, since it said how far, that refers to really the distance. So you could just say like 10 meters it fell, right? The negative just means it went down 10 meters, okay? Make sense? Or almost 10 meters, 9.6. Now, the last part, though, is where you got to consider, and this is what's probably the most missed part over the years on this problem. You got to consider that the helicopter was still rising. So back to my diagram. So this thing, from this level, which was the drop point, this ends up being almost 10 meters in part B is what we found, right? From here that it fell. But it asks in part C how far below the helicopter is the bag, not just how far it fell. It's not the same answer. B and C are not the same answer because the helicopter kept rising. It's really easy to find the rising helicopter because it's going at constant speed, right? So the helicopter also rises for 2 seconds, right? The same amount of time. Make sense? Same amount of time the bag fell, it rose for those 2 seconds to find out how far after 2 seconds. So basically, we need to find this D from here to here, right? And once we have that, that makes this kind of like a two-part problem, doesn't it? At least this portion of it, right? So D of the helicopter, I'll just write DH there, is going to be equal to the V of the helicopter times T. So that's 5 times 2. So in those 2 seconds, the helicopter also rose that much. And the bag fell that much. So here's what we got to do, though. We're not saying that it didn't fall downwards, but we're just using how far, which means distance. Distance doesn't care about what? Direction. So we ignore the negative that came out on this one. If we just want the total distance between the two, we add their magnitudes, right? Magnitude just means a number. So total D between the two, we just add those up, only their magnitude. It's going to be equal to 19.6 or close to 20 meters. We just add those together. That's definitely the trickiest one. Not that we didn't see anything like this before, but there were some things that maybe you could easily overlook. Again, like the raising of the helicopter still, and the fact that VI was 5, not 0. That's probably like the two biggest mistakes on this problem I usually see. You get past those ones, it's not a bad problem. You okay on this one? All right, more. We got time. What else we got? I'll pick one if you guys don't. Yeah. Okay, that's the one I was going to pick. It's really, really similar, 95 is, guys, to 91, which we already did. I don't know if you remember this, but I kind of way back when we did do, not that far back, but when we did do two-part problems, I warned you of something. Like for these problems where somebody jumps out in front of you, we could never confirm if we hit the person or not, or the thing, the object or not, unless we know how far out in front of us it is, right? Make sense? So this problem tells us how far in front of us the thing is. We still do it just like we did 91, or the old example. But in the end, we have a number to compare it to. So if our total distance is beyond this number, we hit it. A total stopping distance, if it's shorter than that, we didn't. We just got to make sure the comparison number of how far the thing's out in front of us, we don't actually use in solving. We solve like we normally would and compare our answer to it. That's the most important part of this problem. Does that make sense to everybody? Watch as I do it. So the driver of a car going 90 kilometers per hour, we're going to have to make a conversion. So that's another reason this is a good one to pick. Suddenly sees the lights of a barrier 40 meters ahead. It takes the driver 0.75 seconds to apply the brakes. So there's that reaction time, right? That we stay at that 90 kilometers per hour for before we actually brake. So this one again is constant V. While we're processing that during that reaction time, then we're going to slow down and decelerate to a stop, or at least try to. All right, so the constant V is 90 kilometers per hour. Let's convert that right away, because that needs to be changed to meters per second, right? Remember what we got to do? I'll do it out in case we forget. 90 kilometers per hour, we could use that little factor label method. And we want to get rid of kilometers and change them to meters. So it goes down there, so it cancels out. There's 1,000 meters in 1 kilometer. Then we want to get rid of hours, which needs to go up top and change to seconds on the bottom, so everything cancels out. How many seconds are in an hour, guys? Yes, 3,600. The number we should know by now. All right, so that essentially means take 90 times 1,000 divided by 3,600. On the quiz, most of us converted correctly, but there were a few out there that didn't. You got to make sure you know how to do this, okay? That comes out to 25 meters per second. So that's my V in meters per second. All right, that's my constant V I'm currently going at while I'm processing the fact that there's a barrier this time out in front of me. I just noticed it, and I travel at T equals 0.75 seconds at that speed of converted 25 meters per second. Then I finally hit the brakes. So just like 91, that V becomes my VI of this part, right? Once I do hit the brakes, that was what I was traveling at. I'm going to try to stop because I don't want to hit this barrier, right? And it gives me the acceleration rate. They do put a negative for me on this time. If they put a negative, I don't have to question it. Sometimes they don't, okay? Meters per second squared. Just, again, remember, did I use the same T over here? No, absolutely not. That is not a stopping time. That's a reaction time. That's once I do react, that T's irrelevant once I start to stop, right? Realize that. Understand it. Don't just throw things around because they're there, okay? So now, like I did in the other problem, I need to find the D of this part and the D of this part. This one's just V times T, and this one's going to need the other equation. Let's throw this in. So this is going to be 25 times 0.75. 25 times 0.75 is 18.75 meters. Now, one other big thing. How far ahead of me is the barrier? I didn't write it down because I don't need it as a given. It's just a comparison number. But how far is the barrier in front of me, guys? Yes. 40 meters. Notice, did I put D equals 40 meters in either column? No, if you do that, you're going to royally screw up the problem. We need to find the D and compare it to that. Just like we found the D back in problems when we didn't know how far it was. Does that make sense to everybody? All right, that's another, probably the biggest mistake on this problem I see, trying to use that D. You don't use it until the end where you compare it. All right, so if you think right now, we're kind of getting close to in trouble because 18.75 is almost halfway there. We still got to find the other one. VF squared equals VI squared plus 2AD. VF is 0. D equals negative VI squared over 2A. Plug in those numbers. And the D for the second half, the actual stopping portion, is going to be 25 squared over 2 times negative 10, right? We run those numbers, 25 squared, essentially divided by 20, because the negatives cancel. We get 31.25 meters as D2. And then like we've done in the past, we add these together, right? So 31.25 plus 18.75 is going to be exactly a total D of 50 meters. We did that in 91, but now we could actually say, did we hit it or not? Clearly we did what? Yes, we hit it because 50 is greater. This is the only part where that 40 comes in. We never used it anywhere else. We got to understand, to answer the question, we found that as normal, and yes, we definitely hit it. That proves it. All right? You okay on that one? What time is it? Oh yeah, so I messed up. We got time for more. Anything? I mean, I think you guys already asked all the ones that there's usually mistakes on, most, so that's good. I'm going to pick 102, just because there was enough people that asked me already about that, that's from the last week. So I'm going to pick that one to do it. I'm going to stress again stuff when we learned about free fall for 102. That use symmetry if you can, all right? If it takes 6 seconds to go up and down, how long did it take to go up? Yeah, 3 seconds, right? So that kind of idea is something you got to use in this one. And to answer 102 in the order that's presented, you have to take it a certain way. Remember something else I said back when we first learned about this. When we throw something up that comes back down, we could take 2 different views on it. Whatever helps us the most to solve the problem. I could solve on the way up, or I could solve on the way down, right? I could segment it into either half as necessary. To answer part A without doing part B first, you have to take a certain way. Otherwise, it can't be done using only givens. All right? So let's see what we got. It says you throw a beanbag in the air and catch it 2.2 seconds later. So that's the whole time, right? So let's just consider something right now. If the whole time takes 2.2, half of it takes what? 1.1. Consider that. How high did it go? All right, so we'll draw this thing. I'll draw a diagram in a second. It doesn't seem like there's a lot of information there. But when we think about it, we got some stuff. We know that the T, one way or the other, is 2.2 over 2, right? Like we just said, 1.1. That's for either on the way up or on the way down. Everybody understand that? Because that was the whole time. It's free fall. It's not going to tell you, G, you should know it, right? If something's thrown up, dropped, or thrown down, G is always a given of negative 9.8 meters per second squared, right? Now here's the other problem. It never told me the initial velocity that I threw it up at, did it? So I got an issue right now. If I try to solve on the way up to find the D, how high it went, I don't have enough information, do I? Now, I could put, I'm not going to, but I could put VF's what on the way up. What does it have to do at the peak for a moment? Yeah. Stop. However, here's why that won't help me. Remember, VI is in all four equations, isn't it? Even knowing VF is 0 at the peak, I have, since VI is in every formula and I don't know it, I still have two unknowns, right? So no big deal. How high it goes would also be how far it fell down, right? So let's think about the trick to this one, using only givens and not solving for anything else first, is to use on the way down. We're allowed to take advantage of it. So if we use on the way down, here's why that solves my problem. Still at the peak it has to stop, but now the peak isn't my final. If I start the problem there, now VI is what? Yeah, 0. I just start the problem from there. I'm completely allowed to do that. G is still negative 9.8, and it's still going to take 1 second to come down since it took that to go up, right? So if we do that, use that with those values, then I could use equation 2, which says D equals VIT plus 1/2 GT squared. That's gone because VI is 0. Therefore, we get 1/2 times negative 9.8 times 1.1 squared. This is the only way to do part A with only givens. You could solve for VI first, but that wouldn't technically be an only given. And we're always attempting to do that if possible, right? So we run these numbers, and I get about 5.9. I did that quick. Let me just double check I got that. Hold on, let me rerun that. Yeah, that's right. Sorry. I get out about, it comes out negative because since I solved it for on the way down, the negative represented went down 5.9. But technically since it said how high it went, well, if it went down 5.9, it must have went up 5.9 to begin with, right? So to answer correctly, we probably shouldn't, like in the way it's asked, we should probably not have the negative on it, right? But we use symmetry knowing that if it went down that much, it must have came up that much. That make sense? All right. So part B then says, what was its initial velocity? Remember, we didn't know it, but now we could use on the way up. All right. For this one, let's see this way. The reason why that's going to help is because the VI is going to be the unknown. The T is still the same. I'll write it down again, even though it's above. 1.1 seconds on the way up. It's still in free fall, right? So this time we make VF what? On the way up, VF is what? When it gets up here. 0. Right? In that perspective, on the way up, that is. But that allows me to solve for VI. That was a problem in part A, but since it's directly asked in part B, we could use all the on the way up and solve it. So VF equals VI plus GT, VF 0. So we rearrange this simply by subtracting over G times T and plugging into that. Negative times a negative 9.8 times 1.1. Negatives will cancel. We get 9.8 times 1.1. And that's about 10.78 or 10.8, depending on how you rounded, meters per second to get the V. Very close to 11. The book answer says, right? Does that make sense? So the best thing of that problem, the reason why I picked it, is to remember you could segment a problem, especially a thrown up problem, into the first half or the second half as needed to solve for whatever you got to solve for. Any other quick questions? There's still 2 minutes left. All right, I will still post this video. Here's what I'm going to do. I'm actually